Suppose summation an x bar n has a positive radius of convergence r, then we can define f from minus r to r to the real numbers, which is the limit function. What we have established in the last module is that f is differentiable. On minus r. Not only that, f prime is given by the series summation n an x bar n minus 1 n equals 1 to infinity. We have this also. So which means recall that the radius of convergence of this term by term derived power series is the same radius r as before, which means f prime is also differentiable. Inductively, we see that f is a smooth function on minus rr. So any function that is defined as the limit of a power series is going to be a smooth function. Now consider the Taylor series. I should put T with a capital. Taylor series T of f, which is just, if you recall, summation nth derivative of f at 0 by n factorial into x bar n. Okay, n equals 0 to infinity. Look at this Taylor series. This is also a power series. Is this series related to the original series summation an x bar n? That is a very natural and straightforward question. Well, in fact, the original series is nothing but this Taylor series. How do you see that? Well, observe that setting x equal to 0 in summation an x bar n, we get f of 0 is equal to a naught. We are all familiar with this. So at least the Taylor coefficient of the first term in the Taylor series and this first term in the power series certainly coincide. Now what about the derivative? What is f prime at 0? We know that the derivative is nothing but summation n an x bar n minus 1 n running from 1 to infinity. Okay? With our convention that 0 par 0 is equal to 1, this leaves us with a1. So f prime of 0 is actually equal to a1. This is a good sign because the second coefficient of the Taylor series, the second term in the Taylor series, coincides with the second term in the power series summation an x bar n. Well, what about f double prime at 0? Well, that's just summation n equals 1 to infinity n into n minus 1 into an x bar n minus 2. So this is actually n equals 2 to infinity. And of course we have to substitute 0 in the place of x. And by our convention what we get is 2 a2 is equal to f double prime at 0. Okay, you can see where this is going. We see that the nth derivative at the origin is nothing but n factorial an. Okay, is n factorial an. In other words, an is nothing but fn at 0 by n factorial, or in other words, summation an x bar n is nothing but the Taylor series of f. Okay, so net upshot is summarized in the following theorem. Everything that we have done is summarized in the following theorem. Let summation an x bar n have positive radius of convergence r. Then so I will write f equal to, with the understanding that f is the limit function, then f from minus r to the real numbers is a smooth function, Furthermore, the Taylor series of f centered at 0 coincides with summation an x bar n. Excellent. Now let me just make one remark. Everything we have done holds true with appropriate change in notation, to series of the form summation an x minus x naught power n. X naught is a real number. So whatever theory we have developed, whatever theorems we have, can also be proven with just a change in notation for series that are centered at a point different from 0, namely the point x naught. We have concentrated for series at 0 because there is essentially nothing that is lacking in our approach. Everything that we have said generalizes in an easy manner, so why not just do it for the easier case and leave the notational changes to the student. Okay, let me make one definition. Let f from AB to R be a function. We say f is real analytic if for each x naught in AB we can find a power series summation an x minus x naught power n whose radius of convergence, of course what I mean by radius of convergence here has to be appropriately changed to take into account that the center is no longer at 0, but that's a trivial change, whose radius of convergence r is greater than 0. We can find a power series summation an x minus x naught power n whose radius of convergence r is greater than 0, and f restricted to minus r intersect, not minus r. I just said that notation has to be changed, but I myself am stuck in the older notation. It is x naught minus r, x naught plus r intersect AB. So you look at this point x naught, look at x naught minus r, x naught plus r, that will be an open interval, intersect that with AB. This is in fact equal to summation an x minus x naught per n. That means, in other words, In other words, in the common domain of definition of the series' limit and the function f both agree. Okay, so on the right hand side, I'm just treating this as a function. I'm just treating it as a function, not as a formal series, but as a function. Okay, so real analytic functions are those that are locally expressible as a power series. Now, it is very easy to see, that examples first, polynomials are real analytic. This is very easy to see. I leave it to you to check this. Now, you might be thinking that there is another obvious example. If summation an x bar n has radius of convergence r greater than 0, then if f is the limit function, then f from minus r to the real numbers is real analytic. Now you might think this is the next obvious example. This is definitely an example, but whether it is obvious or not is not, it's certainly not obvious to me. It requires a proof and I am not able to find any simple proof. Every single proof requires some or the other machinery. Okay, so let me just make a remark about the proof of this. There are several ways to prove it. I'll list 3 ways and not give any one of the ways because this is just a tangential point to our course. So ways to prove this is the following. First way is to algebraically manipulate the Taylor series of f centered at x naught in minus r and show that it converges to f, or rather first show that it has non-zero radius of convergence, and it converges to f. Now you might think, what am I saying? Didn't we just prove that? Right here? No, we didn't. We have shown this result with the power series centered at x naught, right? We have given a function f whose power series is centered at x naught and we have shown this result. Now when you take this new function f, which is defined by a power series, we now know that this power series is going to converge in minus r. If you take a point x naught in minus r, there is absolutely no reason to expect the Taylor series at that point centered at x naught to converge at all, let alone converge to f. There is absolutely no reason to expect that. The fact that it happens requires a lot of algebraic manipulation. You can do this. It's not very hard, but it's still a bit tricky. You can do this. This is one way of doing it directly. Two, show under some general conditions, when a function f is real analytic. Okay, this is a more conceptual proof. Given a function f, can you determine whether it's real analytic or not in some other way? Essentially what you will be doing in this second line of attack is to show that there is a necessary and sufficient condition on the behavior of the derivatives. You can show that under an appropriate growth condition of the derivatives, the function f will be real analytic. Again, this proof is also a bit tricky. Third proof is the proof I like and the proof that I cannot possibly give. 1 and 2 it is possible for me to give, but since it's tangential to the course, I am not. Third is impossible to give. Use complex analysis. This is my favorite. use complex analysis. And this is the most conceptual and according to me the correct proof. Only problem is you will have to develop at least a month's worth of complex analysis to have the tools to show exactly what we need. Okay, so I'm going to leave this as a suspense thriller movie, leaving with no ending, no proof for this, but it's not really needed for this course. It's good to know what a real analytic function is, and I'm not providing any example of a real analytic function apart from polynomials. Okay, so this concludes this module. This is a course on real analysis, and you have just watched the module on analytic functions and Taylor's theorem.